Thank you everybody for being here today at the CRPC meeting. And we are very happy to welcome with us tonight Peter Gaube. Peter is a principal oceanographer at the Applied Physics Laboratory at the University of Washington. And as Tony mentioned already, he will be talking to us about the salinity and stratification at the sea ice edge, which is a NASA approach to physical oceanography in the Arctic. Peter, the floor is yours. You will briefly introduce yourself that you told me, so I will let you do the rest. Thank you, everybody.
Great, thank you, Gianluca. Yeah, I'm Peter Gaube, University of Washington, and I am new to the Arctic community, so I am learning on my feet here, and it's been really exciting. It's been very welcoming to get to learn about all the fascinating stuff that's been happening up here long before I started to get to have the opportunity to focus. So I'll be presenting on the SASSIE project, and I wanted to appreciate Tony's land acknowledgement. And I wanted to mention in the SASSIE project, we did a very poor job with engaging with local communities prior to doing our work there. And we've learned a lot, and we'll be doing it much differently in the future. But unfortunately, we were not ready to do that correctly when we did SASSIE. But just wanted to put that out there on the table. I'm gonna go ahead and start my presentation and share my screen here. And then I'm gonna just go ahead and ask Tony to let me know if it's not working and if you guys just see presenter mode or not, but let's see. Okay, Tony, are we good to go or do I need to switch it?
So we still see, okay, now we see presenter mode.
There we go, okay. So this here is a presentation that's gonna talk about the actual experiment, the salinity and stratification at the sea ice edge experiment, and give you some information about the measurements we made, where the data is available. All of our data is now publicly available. Some of the tutorials we've built to help people use our data. And then we'll talk about some of the projects that are ongoing because we are now in the data analysis and inference phase of this mission. This background video that hopefully is not giving you a headache is a drone view of the RV Walstad, which was the ship we took up into the sea ice in the Beaufort Sea. And here where we are pushed up against a large piece of ice that we are installing instruments in. This was a NASA funded project, and this is a joint presentation from the whole science team. So why SASSIE? Well, I'm preaching to the choir here. Here is an image of the minimum sea ice extent in 2022, which was when we were in the Beaufort Sea, which you can see from that kind of box, which is where the SASSIE experiment happened. We were there for the entire month of September, so we were there for the sea ice minimum. We did that on purpose. And so in the image, you see the sea ice minimum, and then the yellow line is the 1981 to 2010 average minimum, showing that if we had done this experiment prior, we would be in the sea ice and not even be able to make the open water measurements that we were focusing on. So this is one of the reasons why SASSIE, because polar sea ice is disappearing at a very dramatic rate. Also, the poles are heating at a much higher rate than other parts. And I use that generally, it's not the poles, but this part of the Arctic is heating quite quickly. So here we are looking at the surface temperature anomaly, and that's the anomaly in 2022 in January against January 2016. So just in that short period of time, we have anomalies approaching 6 degrees Celsius. So the Arctic is warming, and that's one of the reasons we wanted to go up there, because we want to see what the effect is of melt on stratification, and therefore the effect of stratification on refreezing. So let me briefly describe the SASSIE idea and the different phases. So we broke apart the sort of ice melt and refreezing into 3 phases. So sometime around August, we have a lot of melting. We're approaching our minimum time. And what we see is we expect to see some anomalous, maybe fresh water at the surface from the melting ice. As we go into the sort of minimum ice time, we have open water where there was ice before, where we have the ability of wind to break down stratification, as well as any cooling events that could break down stratification. So the stratification we might have seen forming during melting ice might in some places be broken down, some of it might sustain. And if some of that stratification stays and some of that fresh water is held at the surface, we expect that to either increase the rate of ice growth or the date at which ice starts to grow. So the SASSIE hypothesis and the main goal was around the idea of we wanted to understand how near surface salinity stratification modulates refreezing, with the hypothesis that regions where stratification is able to persist and fresh water is trapped at the surface by the strong halocline, we would expect those to refreeze a little bit earlier. So that's the general overview of the idea. We did this in 3 different missions. The first one, we sent out autonomous wave gliders and ice buoys in early August. Those navigated from the north slope of Alaska into the Beaufort Sea, and we're taking continuous measurements of meteorological properties, but also of surface stratification, primarily looking at salinity, so multiple salinity sensors on the vehicle and then down on the tether, giving us profiles. Those were navigated into the central Beaufort Gyre, where we then met them with the, this is actually, the wrong name was actually the Wallstad, not the Norseman, where we conducted sub-mesoscale resolving underway CTD surveys, along with larger scale mesoscale surveys, while also attending to multiple autonomous vehicles that we'll talk to and using those to make measurements. When possible, we were joined by an airplane flying in from Dead Horse, Alaska, that had the PAL sensor, which is a passive active L-band radiometer that gives us measurements of salinity. And so we have salinity measurements from an airplane along with this. And then we left a number of assets there in the ice to continue to make measurements into freeze up. So SASSIE used a number of different autonomous assets. One of the ones that we built for this particular mission is this autonomous jet ski here. It's actually a kayak powered by a jet ski, and it was used to measure near surface salinity stratification where it would be too affected by the large bow wake of the ship. So as you can see here, it has a hose coming off the side. That's a salinity snake, which is an instrument we also have the ship that sucks water from the surface, gives us a true surface salinity value. And then below, it's a little hard to see here, there's a keel that had 4 different CTDs. So over the upper meter, we had 5 measurements, including a surface measurement from that autonomous vehicle. In addition, as I mentioned, we had wave gliders, which we deployed from the North Shore, then rendezvoused with. Because we were in September, we didn't have sufficient solar radiation to keep them charged with their solar panels, so we had to charge them on deck and then release them again, and they would go out for about a 1-week mission. Additionally, we had an under ice float. This is a neutrally buoyant isopycnal float that can be controlled to sit on specific isopycnals. It then profiles, taking very high resolution CTD profiles towards the surface, has an upward facing radar, so it can tell if it's encountering ice, and if it does, it takes a picture of it. And then it goes back down and it comes back up until eventually it can surface, and then it sends all that information back over the Iridium network. And so what we see here on the left are under ice pictures made by the under ice float here in the right, held by Jim Thompson. And these are currently being analyzed, and I'll talk about a project with that to sort of understand temporal changes in the ice field. And then we also had an entire fleet of Swift buoys. These are buoys that are deployed. They sit at the surface. They measure the wave spectra, meteorological properties, as well as upward facing ADCPs, giving us near surface currents. They were also equipped with CT sensors, so we have salinity, and we would deploy these 6 to 8 at a time, and we'd have an array of them drifting that would then have to be recovered. So in addition to the autonomous vehicles I mentioned, we also had the RV Wallstad, which is shown here next to the ice, showing some of the different instruments we had. We had a series of meteorological sensors. We had the ship S-band radar, which we were actually using to do some information about classifying how much ice we were in, but this is nothing special. This was just what's on the ship, but we used a screen capture device. We had radiometers, and then we had an underway CTD that we custom built for this that we used to collect very high resolution profiles behind the ship while underway. And then, yes, the salinity snake being the key measurement here, because we're taking true surface salinity measurements. Because the stratification in the Arctic is so strong, we saw some very strong gradients in the upper meter, and we're trying to measure surface salinity to compare it to the L-band system on the airplane, and then also the satellite sensors. I'll remind you that this was funded by NASA, so that is why we are doing quite a bit of work to look at measuring the surface. On the left here, we see the different flights that were conducted, doing different patterns, including larger surveys, smaller surveys, interspersed surveys, and these large from the sea ice to open water surveys. On the right here, we see the track of the ship, and shown as salinity, and we spent quite a bit of time up in the ice, and then we also spent time in the open water trying to compare these two regimes to understand how stratification might modulate the refreezing in these areas. Now, the SASSIE expedition was designed to be adaptive to ice and weather conditions. We did not have an icebreaker. We were able to go into the ice, but we were able to break it or anything. And with a number of the assets we were deploying, we really needed some decent or favorable weather conditions to deploy these. So what we decided to do is to go into SASSIE with a playbook. We spent quite a bit of time before the expedition coming up with a series of surveys we would do from 1 to 2 days that would address specific parts of our hypothesis and help us get the measurements that we need to address certain questions. And then the playbook was organized so that we could kind of go by what are our conditions. Okay, we have 2 days of really bad wind, so we have to head into the sea ice. What can we do in the sea ice? And so the goal there was to be able to maximize the time out there without having to waffle around on decisions, or to be able to have a playbook to go to quickly make adaptive decisions. And that was something I learned from SASSIE. That is something that would apply to any other future seagoing oceanography, is to really have a lot of ideas laid on paper ahead of time so you know what you can do without having to think about it and modify from there. All right, so that was an overview of the different measurements. Now I'm going to move on to the data, and behind those data, the people who made the data, who collected it, who processed it, made it publicly available, and the people who are now analyzing it. And we're going to talk about some of the projects that are ongoing. So on the top, this is the whole ship crew. There's about 20 of us that spent a month together on a converted Alaska crabbing enforcement vessel. The vessel originally had 2 staterooms, but they converted the crab hold into science quarters so that we were able to fit 20 people there. It was very tight, but it worked out just fine. This here is our aircraft crew from JPL, and they were working here out of Dead Horse, Alaska, flying on this airplane. And then we just have a number of pictures from the expedition, including our after the expedition science team meeting here in Seattle, Washington. So one of the things that is maybe a little different with SASSIE is we were really pushed to have all of our data publicly available within 6 months, if not earlier, from returning to the dock. So as soon as we got back, we spent a lot of time getting the data quality controlled and making tutorials and helping people figure out ways to access our data. The reason we wanted to do this is that this data is very valuable, it's timely, and we can't be possibly the only people who can ask good questions to this data, so we wanted to make sure that the community had access to that. So all this data went onto the PO distributed archive, PODAC, the NASA PODAC, which is on the cloud and available from anywhere. It's free to access. All you need is an Earth data account, which is a free account to make. So you can get the data that way, but we wanted to describe the data. So we actually spent quite a bit of time building an outreach website called the SASSIE Data for You website. On this website, you can click on any of the different data types we have across the top. As you go down, there'll be a video from the person who collected the data describing the data and how to work with it. There'll be example figures made of the data and a description of sort of the data files and the time and physical extent of the data. So that's the SASSIE Data for You website, which is kind of an interface to help people find the data and to see what can be done with it. The second part is we wanted to reduce the barrier to entry to data analysis. We're now in an open data time where we are encouraging people to build software packages that are publicly available, that are usable instantly, and that are usable on software that is free of charge, that is open source. So in this line, we decided to build a SASSIE Code for You repository on GitHub, along with a storyboard that sort of walks you through it. And this was done by our programmer who joined the project, who came straight from undergrad and actually got to do the experience of working with ocean data for the first time during SASSIE. One moment, please, okay? Okay. So on this SASSIE Code for You website, there are Jupyter binders that actually run the code, that download the data so you can see it all happening live, and it's just right there on the website. And every one of the figures that we used in the SASSIE data paper, which describes the whole cruise, were produced using the code on this website. So it's nice because it links a published paper with the figures to the code that made the figures. And what we really liked about this, we got some great feedback from incoming graduate students who really enjoyed being able to see this and use this even to analyze their own data, just to have a baseline of some code to do some simple plotting analysis. So the first two deliverables from SASSIE were the data and some code on how to use them. And from this point forward, it's been really a great community effort to work with this data. We have the core SASSIE team, but it continues to grow as people contact us as they're using the data. All right, so what I want to do now is talk a little bit about the type of surveys we did. So here we have a drone video of the JET SSP, which is the jet ski powered surface salinity profiler. We were able to use this to go and survey right up against pieces of ice, look at sort of the spatial distribution of near surface salinity stratification and how that's influenced by large ice, small ice, or even regions where it looks like we have melt puddles. Now, these surveys were also done in conjunction with the research vessel. So quite often we would run the two vehicles next to each other, giving us a profile of salinity from the true surface with high resolution in the upper meter. And then we had the ship's TSG, and then we used the underway CTD from 5 meters down to 150 meters. And what we have is a complete profile of salinity and stratification from the surface using a number of intercalibrated instruments. All right, so what I'm going to do now is just present a couple different slides of some of the different analysis projects that are happening and some of the folks who are doing them. So as I mentioned, we have stratification data from the surface down to 100 meters. So on the top left, we can just see a very strong submesoscale front in the near surface that was measured by the JET SSP. We were not able to see any evidence of the steepness of this in the ship because it was so well mixed. So we see some neat gradients. We're now starting to look at the differences in surface salinity stratification near the ice to see if we can make some predictions on when the ice should refreeze. Another thing that is being led by Carlin Schmidgul, who is a graduate student here at UW, who was on the expedition. She's shown here on the right holding the underway CTD profiler that we built for SASSIE. And here's just an example of a couple different salinity sort of stratification regimes she's identified in our data, and she's looking at, in particular, sort of the strength of the halocline and how that modulates heat transport and how that might affect freezing. Also on the right is our fearless leader, that's Kyla Strushka. She was the chief sci on the SASSIE project, and she sort of helped us make all our decisions at sea. Using the under ice float, Melinda Webster, along with Andre Sherbina and Eric DeSaro here at the Applied Physics Lab, are starting to develop a machine learning algorithm to classify different types of ice and then be able to go into the data set with classified ice and look at the stratification and the heat fluxes and try to understand the vertical upward flux of heat or the trapping of that by freshwater lenses and how that modulates the type of ice and the thickness of the ice. So this is an ongoing project, and this was one of the assets that we left out there, and it worked well into freeze up until at some point it couldn't pierce the surface anymore, and that was it. Using the PALS instrument together with the satellites, both SMOS and SMAP, we're doing a very complete comparison of in situ versus remote sensed salinity. And we're seeing some interesting biases. We're seeing the effect of vertical stratification. We're seeing the effect of bias on the satellite measurements near ice, things that were often thought to be corrected, but we're actually still seeing that there's quite a bit of uncertainty in the satellite measurements. And this has been really only been possible because of our real efforts to collect surface salinity. And so if we compare this to the surface salinity snake versus anything below, we do see big changes in the bias offset from what we see from the satellite. And in this image here, you see the airplane and then the JET SSP all working together. It was fun to try to coordinate all this. All right, in addition to the work that Carlin's doing and sort of looking at some of the classification, she's also looking at submesoscale near surface salinity and density fronts that propagate along either the marginal ice zone, or we saw some large eddies filled with Pacific summer water that was quite a bit warmer than what we saw earlier. So she's trying to understand some of the variability in the Pacific summer water and some of the heat that would be available for melting or for the prevention of further ice growth were the haloclines in the region to be mixed away by a storm event or something like that. In addition to looking at the data directly, we're also using our observations of the near surface stratification, particularly salinity, to force 1D models to try to understand sort of the 1D effects of this. This is work being led by Julian Schuntz at Earth and Space Research. And so here on the example is just 2 different 1D models. I think this is the Gaube model, forced with, at the top, a profile from the open, let's see, that would be the open water profile. So that would be over here where we see lower density stratification in these boxes, compared to a profile that was up in the marginal ice zone where we saw very strong density stratification. And if we go ahead and let this model go forward in time, what we see, and I know this is labeled incorrectly, it says linear salinity, but this is actually an open ocean profile. We see that the open ocean profile freezes up at a later time, and it also just has this more effort to lose that heat. So what we kind of see here is some sort of suggestion that our hypothesis that near surface salinity anomalies could act as a way to increase the rate of freezing, or maybe just to increase the or move up the date of freezing. That indeed that near surface stratification could play a pretty important role in that. And so this is ongoing work we're pretty excited about, and we're doing this in conjunction with quite a bit of satellite analysis. Early results from the satellite analysis pre-SASSIE, before we went out there, and then looking at the data while we were out there, we're in some ways hampered by the satellite products having some real issues with sea ice contamination, and some of the sea ice products we were using not being high resolution enough. There is now a NOOS satellite SSS product that promises to be a little better in terms of ice contamination, and we have a new sea ice product that was derived here at UW from the sick ice charts. But just an early result, you can see here on the x-axis is salinity versus SST, and we marked pixels in red that did not turn to ice in the next 21 days versus pixels in black that did. And you can see in general the pixels that froze earlier were fresher than those that did not. So this is just sort of pointing towards the general idea of the role salinity has, but this is an ongoing analysis where we're really trying to understand, can we predict if a patch of water will refreeze based primarily off its salinity and presumed stratification. And we have 2 different students working on wind-wave interactions and air-sea fluxes, primarily from the SWIFT buoys shown in the bottom right. Shown on the left there is E.J. Rainville, and then Malcolm Leclerc was not on the expedition with us, but they will both be looking at these data sets, and they're being guided by Jim Thompson. And this is the integration of all of the different autonomous vehicles to really understand sort of what is the effects of changes in the marginal ice zone, near surface stratification on wind-wave interactions, and the transfer of energy into the ocean from the atmosphere. All right, so I gave kind of an overview there of some of the different things that are happening during SASSIE, and my goal here was not to kind of give any kind of deep digging into the science we're doing at the moment, because it is evolving, but I really wanted to open this up as a conversation with the community here to sort of hear what your questions are about the experiment, or if there's anything you'd like to share about things you saw that we did that we could do better. I'm just really interested to hear, because as I mentioned before, I'm new to the Arctic community, so this is a very exciting project for me to sort of learn about all the basic things that I've missed over the years.
Thank you, Peter, for your talk. Amazing data set and amazing effort, I think, to put it online and make it available to everybody in the community. So that is great, I think. And so if anybody has questions or comments, as Peter said, please go ahead. You can, I don't know if, I think you can just unmute yourself and speak, probably.
Yeah, people are welcome to type questions in the chat if you have them, or raise your hand can also be a nice way to do it, or you can just come off mute as well.
Oh, I have a question. Thanks, Pete. It's great to see that data. So one quick question I have when I see like you showed the cruise track with the sea surface salinity from the ship, and there you can see that there are higher sea surface salinity outside the ice relative to inside the ice, which is kind of the opposite of the cartoon that you show, or the kind of the first idea that I guess SASSIE was built on. So I was just wondering if you have any idea why there are these contrasts in salinity that are kind of not quite what we expect from meltwater.
Yes, that is a good point. So I think when we approach this with this general idea that there would just be fresh water in the meltwater, fresh lenses at the meltwater, I think that really didn't take into account the roles that stratification would have in sort of either holding that water there or allowing it to sink to a certain level. So that said, what we kind of found in our sort of into the ice and out surveys is, even though at times we did see fresher water at the surface offshore, it was, much more homogeneous throughout sort of the mixed layer there. And so it had kind of mixed through, it had been just sort of mixed around, whereas in the ice where we did see some evidence of melting, we saw that that fresh water was kind of trapped somewhat near the surface by its combination, by sort of its density anomaly. But the water surrounding sort of that ice was quite a bit saltier. So it's interesting to see that even though there's fresh water put into it, it was saltier water than offshore, even though it was having fresh water put in. And we believe initially that because part of that was that water that ice was sitting in initially was saltier. It's also important to mention we saw the influence of the Mtng River there on a number of our samples. And so there's another part to this, which is the effect of rivers. So it's not just the meltwater and what it can do, but if the existing stratification is causing the river water either to settle at a specific depth or to have a certain amount of mixing influence near the surface. So I think it was obviously a lot more complex than we thought. And I think just that basic idea, like you said, like it turns out we were up in the ice and we saw some salty water, but we also saw some really fresh water in there. And what we really saw was an incredibly strong stratification. And that was kind of the big difference there.
Cool. Yeah, thanks. There are really interesting questions to look at.
Yeah, and we really want to encourage people to look at the data, they're out there. And I think that a lot of people would have certain questions that, that could be explored in the data set that we certainly are not using it for.
I would pop in with a question if I can. You mentioned you had some ADCP measurements, some current measurements, right, together with salinity and temperature at the same location, right? It was the same instrument doing all the measurements. Is that right? Can you tell me a little more about the instrument and what kind of data you get out of there?
Okay, so ADCP, the only ADCP we had was on the ship, and it was a standard 300 kilohertz workhorse Teledyne ADCP. And then on the ship itself, we also had the TSG and the sea chest, so sort of a standard equipment there measuring temperature and salinity. But what we brought along was the surface snake. So that's an entire system that measures that. Then we also brought along an underway CTD profiler. So it's not that everything was housed together in one thing. So that's for on the ship. In the autonomous vehicles, so there were the Swift buoys that had ADCP on them, as well as a CT sensor and an IMU to measure wave properties. So those are existing Swift buoys that are made by Jim Thompson here at APO, and they exist in different forms with different levels of instrumentation. These were the ones that also had the salinity sensors. The wave gliders themselves also had ADCPs. We put salinity sensors not only at the surface, but we also put them down on their drogues. We had a lot of issue with the ADCP data. And I bet you that a lot of the polar people here are kind of laughing because they're like, yeah, I could have told you that. But we really had some issues, so much so that the shipboard ADCP, we were not able to recover currents from it because the company that owns the ship that put the ADCP in had it nicely commissioned and everything, but they had it commissioned at lower latitudes. And when we went to the higher latitudes, the compass headings they had weren't sufficient to be able to back out the ship movement. So that for the ship-based ADCP, we have measurements of shear. The wave gliders had a very similar issue, is when something's moving like this and you're so close to the poles, to try to get the heading correct is really hard. So I learned the value of satellite compasses, and then I'll always have one on my ship.
Good, thank you. I will definitely look at the data anyway, so that's
Yeah,
that's
yeah,
very
absolutely.
interesting. Thank you.
And then as people are sort of thinking of questions, I would like to pose a question to the group. And it goes all the way back to sort of how I started this, and saying that when we did SASSIE, we approached it from what does NASA want to know? How do we measure it? Let's go out there and measure it. That's not really the approach we want to take to science anymore, especially when we're working in communities and people who are living in the waters we're measuring. We want to do co-created science. We want to work with the communities there who are facing climate change to understand what their problems are, and to be able to match our science to meet their needs while we also go ahead and accomplish the things that our agencies need. So I would like to hear if anybody would like to share some experiences about working with different communities in the Arctic, and not details, but more so like this went horribly wrong, or this was a really valuable lesson, or something like that, because I feel like that's somewhere where I would like to put a lot more effort before we begin our next Arctic program, is to find an integration with a community where we really feel like we could be making somewhat of a difference.
And in the meantime, I will take advantage of this question to ask actually, what do you think are the next plans for, I mean, do you have already planned a follow-up for SASSIE? I think so. That's what's the future?
Yeah, I mean, don't have
in
a
terms of also
follow-up.
interaction, yeah.
We don't have one planned directly. We're wanting to do a follow-up. We have more questions than we have answers, right? That's the beauty of this type of work. And part of that follow-up would be directly linked to working with a couple of communities we have been working with up there, and trying to link in their desires for remote sensing or their needs for information into our kind of goals. And one thing we'll be focusing more on is rivers too, because we really sort of ignored the river question here, and I think it's pretty important.
I said, no, maybe also Meredith and Tony have some pointers of other people in IRPC that can contribute to the question of working with somebody else. I don't know, but yeah, maybe later.
Well, I do just want to say that really appreciate the question. Our most recent Arctic Research Plan has the deliverables that the different teams are working towards, established participatory research and Indigenous leadership research as kind of a foundational activity that should be underlying all of our work. So there's several deliverables that are about exactly what you asked about. It's like, how are we moving towards kind of co-creation, co-production, and kind of having that as core of a lot of our work. So I think there's like a lot of maybe ideas. Again, I don't know if anybody has maybe a past experience that they can speak to, but I just want to say I love posing that question and to be thinking about it as we're moving forward, because that is exactly the the direction that we're trying to take with it. Making sure that's always kind of like the lens through which we're thinking about it. Any of our work.
Thank you, Tony.
Yeah, we've in the last few months have had some great conversations with different communities and hearing about their needs, and it's really eye-opening to think about. You got to have thick enough ice to butcher a whale. I mean, that is like a fundamental thing, and knowing if that ice is going to be around or where it is really important. So these are the type of things where we can learn from what folks' needs are, and really adapt our science to answer those questions.
About that, are you planning to use your data now in terms of developing models for forecasting sea ice growth? But understanding it is probably the main goal, but is there a plan to use it in models and improve forecasting, operationally, let's say?
Yeah, I think ultimately, yeah, that's absolutely the goal, because what we're seeing now is, for example, the ERA5 reanalysis, which is used by so many of us. I understand it correctly, there's not much in terms of surface stratification there at all. And I don't even know if salinity is a variable or if it's set. So we're trying to understand some of the sort of the magnitude of the effect of some of these near surface stratification regimes you would have that don't exist in the existing, that are not resolved in the existing models. So I guess some of the questions would be like, is it worth making an ocean underneath your atmosphere model that has near surface stratification? There's obviously other questions about the spatial resolution that, SASSIE isn't directly getting into that. There is a modeling part to SASSIE, so we're working with Ian Finty at JPL. He ran an echo solution for us that's very high resolution, and from there we're trying to understand, can we sort of the dynamics in the model are, as far as we know, correct, but are we able to correctly sort of capture the growth of sea ice in a high resolution model? Or even at the highest resolution we're running, is it just not sufficient to really capture sort of the spatial mixing of fresh water, and then also the vertical resolution, is that sufficient to capture the effects of stratification on keeping heat down or keeping fresh water at the surface? So that would be the ultimate goal. It's not part of our program right now. SASSIE was sort of designed as a one-off. And so this is, we're in our final year, our analysis and publication year, but in the future, future programs like this, I think, would have maybe a tighter connection to sort of model development. So beyond just spatial resolution, but really looking at vertical resolution.
It would be super interesting, that's for sure. I mean, I would be interested. Thank you. Is there any more comments or question?
I have one quickly. Yeah. It's kind of related to something you've said already, but I know communities in Greenland that would be really interested in a tool like this one. Do you have any plans to do something along the coast where the communities are hunting, or is there any way that they can use this sometime soon?
And so a tool, are you meaning the autonomous things or just the data?
Well, would they be able to predict or to at least know how strong the ice is around where they live and where they need to go hunt and how reliable it is at a given time?
Yeah. I think you're hinting at sort of one of the things that's motivating sort of our next project. So there's two facets to that. One is obviously the seagoing understanding the salinity stratification. The second one is, how do we measure it from space? Measuring salinity from space is not easy. And the sensitivity of the measurement is inversely related, is related to temperature. So in cold water, the sensitivity of L band microwave radiometry to salinity goes down substantially. So it's really hard to measure salinity in cold water from a satellite. So do we need to know that? And the answer is yes, it's incredibly important there. So that's one thing we have to work on, is new satellite technology. Also to be able to resolve stuff close to land, because you're mentioning these coastal communities. They're operating in a region of the coast where, especially our salinity satellites, just can't function because we have the contamination by land and the L band radiation coming off from Earth. So there is an effort underway to build a new type of satellite to do that. Obviously, that's many years down the road. But then the second question is sort of these kind of science, the experiment we did, the tools we have, how can that be used for coastal communities to predict something about their ice? And I think, unfortunately, I feel like we're just still a little tiny bit too far away from that. Like, and my understanding is we're not quite there to be able to really predict that part of the ice, but I think we're starting to get some of the measurements that will allow us to make those models. That's not my expertise though, but I think that it's a really, it's interesting and fascinating. I think it pushes us towards thinking more about coastal environments in the Arctic. When we think about the relevance to the communities there, we're so often in the past, I've really focused on the open ocean. So yeah, that was a long-winded question to say, no, I don't have an answer.
No, but it's all right. But it's great. Thanks for the presentation. And if you can develop that, I know some people who would be happy to use it.
Yeah, wonderful. Well, I mean, we're really hoping to go work this time again in Alaska, just because of the communities we have contacted there. But I think that, the results that could come from something that, and more importantly, the push to invest in a satellite sensor that resolves these things, that can give you the thickness of sea ice. That's something that's very difficult to do, especially if thin is sea ice, and the L-band is shown to be pretty sensitive to that. So while we make improvements in measuring ocean surface salinity, at the same time, we'll make drastic improvements in measuring thin sea ice, which is a lot of the ice now, as well as soil moisture, which is important to a number of things.
Thank you.
Thanks for the nice talk. I also have a question because on one of your slides, you show that you measure the Mtng water, if I am correct. And I was wondering how often you crossed the Mtng, because from the salinity remote sensing, it is very hard to calibrate the algorithms in freshwater, especially near the coast. As you said, we have issues, and it's very difficult to validate the salinity in the river waters also. So I was wondering if you have an opinion on that, and if you made several.
I mean, river waters in general, I mean, the only way we can say anything about it is just because we did take some Del 18 samples. So we were able to identify some of the isotopes of Mtng water in some of our stations. So we have some basic ideas about that. We also looked at, we had a fluorometer on the ship, so hopefully some sort of humic CDOM was in there that we were able to detect. But this idea of how do you validate salinity measurements in brackish water, I mean, that's honestly, that's beyond my expertise, no, I won't lie, but I think it's interesting. It's also where we really need to have the measurements, it seems like. Having these, very strong salinity gradients in coastal waters, those are huge controls on density, and therefore, have a sort of outsized effect on the coastal flow. So I think the need for understanding the fresh water coming out and how it's mixing is pretty important, I would imagine. But I think it's difficult because of the land contamination, first of all, and then secondly, cold water is really hard. But beyond that, I'm sure there's other difficulties that I don't even understand with trying to measure salinity of river water.
But especially in the Mtng, with from SMOS data, we saw very, very fresh salinity. And I suspect sometimes that it is too fresh, but very, very difficult to validate, in fact.
I mean, the signal's going down with that fresher water and the coldness. It's just probably at really the limits of the ability for the sensors to resolve.
Any other question? Otherwise, I think Tony had an announcement or something, some news.
Yeah, if there are no other questions, and if there are, feel free to pop those in the chat or come off mute. If we've got, we've got a couple more minutes till the top of the hour, so I just wanted to share a little reminder while we've got some folks on the call. But I did earlier just mention about our Arctic research plan, which is a 5-year plan outlining some goals, the priorities for Arctic research issues. And under that plan, we've got 2-year implementation plans that outline like very specific deliverables to ladder up to those broader goals. So just wanted to remind the community, for anybody who maybe isn't aware, that we're currently in the process of updating the implementation plan. So that's going to outline teams such as physical oceanography, their goals and what they're going to be working towards for the next couple of years. So I'll drop some information on the update and form for input in the chat, but the public input period is going through the end of May. So we're in the last month to take a look at the current plan and share any thoughts on objectives, deliverables that we want to continue from the current plan, maybe with some tweaks, maybe as is. Anything that we can close out, maybe we feel like we've accomplished or is no longer one of the top priorities and we want to focus elsewhere, or anything new that, you know, maybe we should think about adding to the next plan. So just want to say that, you know, all feedback is super valuable. This is a publicly available Google Form link for input, so you can definitely share that around with any colleagues, anybody who has interest, experience with Arctic research. You know, the drafters will take a look at everything that is submitted. So, you know, any voices from the community, it's really like an opportunity to just share, you know, what you think about the current priorities, direction, as we look toward the next meeting. But Meredith, let me know if there's anything you would add to that.
You, Tony?
And otherwise, I would just say again, this meeting itself will be recorded. Like I said, the top of the call will be available on the IARPA collaboration site and YouTube channel. And stay tuned. We've got our next meeting on June 6th at the same time slot. So 9 a.m. Alaska time, 1 p.m. Eastern time. Have an event page and agenda for that soon this month. But since we do have a couple of minutes, I don't see Supra on, but if anybody else has anything upcoming and they want to share with the physical oceanography community, got a couple of minutes. Scott, anything that they would like to share or bring our attention to?
Thank you. And so unless there are, I guess, another question or comments, I would like to thank Peter again for his talk, the amazing videos, and even more for all the data which you very nicely put online and made it easy to reach, which is something very rare sometimes in data set. Made it easy to understand and download. That's a very big effort and something which is very, very rare sometimes, but that's great. And thank you everybody for being here. And we'll see you hopefully next month. Yeah. So to see you soon again at our next meeting.
Thank you everybody for the feedback. I appreciate it. It's always great to hear. And thanks for the invitation. It was wonderful to meet most of you virtually and hopefully get to meet you in person someday.
Thank you very much.
Thank you again, Peter.
Okay, thanks, Tony. Bye.
Bye, everybody. Thanks.